am Professor Tushar Gujaratri from S&D College of Engineering and Research Center, Evla. Today we will discuss a topic that is time domain analysis of the system based on subject mechatronics. So let's start. So what is time domain analysis of the system? So those system which depends upon time. There are many systems which depends upon time. So time is used as an independent variable in most of the systems. So that is one independent variable in most of the systems, which is time. So it is usually of interest to evaluate the output response of the system with respect to time or simply the time response. So any system, if you apply input to that system, there will be some output. Okay. So sometimes this output depends upon time. Okay. So we have to evaluate the output response of the system with respect to time. Sometimes we have to do this. Okay. So actually time response is divided into two types. That is transient response and steady state response. Like this, transient response and steady state response. You can see the addition also. Y of t is equal to yt plus yss. In the time domain analysis problem, a reference input signal is applied to a system. Okay, one input signal is applied to system and the performance of the system is evaluated in the form of time domain specifications with respect to transient as well as steady state response. Okay, so what happens in this time domain analysis? We apply some input, reference input signal, and we find performance of the system with respect to time domain specifications. Okay, we'll study this in next slides. So the stable system exhibit transient phenomena to some extent before the steady state is reached. So what happens? Suppose, for example, mechanical system is there. So any mechanical system, any part has some inertia due to its mass. Okay, means what? Suppose one connecting rod is there. We want to move that connecting rod. So if you apply force, immediately it does not move. It has some inertia. It takes time to overcome that inertia, and then that connecting rod moves. Okay, so same thing is written here. For example, in mechanical system, inertia is unavoidable and thus response cannot follow sudden changes in input instantaneously, and transients are usually observed. Transients means what? Some delay is observed. Okay, so control of transient response, which leads to deviation between output response and input response before the steady state is reached, must be closely controlled. Okay, so when you apply input, it takes some times to get output to get stable. So this deviation between input response and output response we have to control. Okay, that should be controlled. So control of steady state response is also very important since it determines accuracy of the system. So for determining accuracy of the system, we have to control the steady state response. Okay, more so with respect to position control system. So in case of position control system also, we have to do accuracy determination with the help of time domain analysis. So this is one graph is shown here. This is called as unit step response of second order system. So let us assume second order system and input applied to that second order system is like this, which is called as unit step response. Means one unit input is applied to this system. Okay, so after application of input, suppose output is varying something like this. It is taking some peaks, something like this. After some peaks, it gets stabled. Okay, so after 2 to 3 peaks, the output is getting stabled. Okay, so in this graph, you can see that on y-axis there is y of t, that is amplitude is shown on y-axis, and on x-axis time is shown over here. So here we can see 3 to 4 definitions are here, or 3 to 4 times are provided over here in this graph. Okay, so you can check that this horizontal line, this is unit step line, that is unit step input whose value is 1, and now we can check there are some different times are shown over here. So you can check this rise time over here, which is written rise time. So what is rise time? So whatever output response is there, it is rising something like this. So time taken by output to reach from 10% value to 90% value, that is called as rise time. So you can check here, here it is 0.9 and here it is 0.10. So 10% to 90% output response is called as rise time. Okay. Now similarly there is delay time is shown over here. So this is delay time. Okay. So from 0% to 50% output response, whatever time is taken, that is called as delay time. Okay. Now here settling time is shown over here, bottom side. So from 0% to up to 95%. Okay. From 0 to 95%, whatever time is required to settle the output response, that is called as settling time. Okay. And here it is shown maximum overshoot. Okay. So this is maximum peak observed during the output response is settling. Okay. So there are some peaks are observed. So this is one peak, second peak, third peak. So whatever peak is maximum, that is called as maximum overshoot. So that peak is called as maximum overshoot. So like this you can see the definitions in time domain specifications. So these specifications are mentioned over here also. So first is percentage overshoot. So whatever definition is written here, that is, it is the amount that the response overshoots the steady state or final value at the peak time, expressed as percentage of the steady state value. So it is the amount that the response overshoots at the peak time. Okay, just we have seen in the graph. So the formula is 100 into e raised to minus pi zeta divided by under root of 1 minus zeta square. So this is the formula for percentage overshoot. So second definition is rise time. The time required for the step response to rise from 10% to 90% of its final value. Okay, up to 90% value, the time required is called as rise time. The formula is TR is equal to 0.8 plus 2.5 zeta divided by omega n, where zeta varies from 0 to 1. And third definition is delay time. Time required for the step response to reach 50% of the final value. To reach 50% response, the time required is delay time. And the formula shown over here is TD is equal to 1 plus 0.7 zeta divided by omega n, where zeta varies from 0 to 1. Okay. Now next is settling time. 2% settling time. So time required for the step response to decrease and stay within plus or minus 2% of its final value. So plus or minus 2% means 2% error is taken here. So 2% of its final value. So this is settling time, and the formula is TS is equal to 4 upon zeta omega n for 2% settling time. And last definition is steady state error. It is the difference between the output and the reference input after the steady state has reached. Suppose steady state position is reached and still there is difference between input and output, then that error is called as steady state error. Okay. So these are the time domain specifications. Now here one example is shown. So suppose natural frequency is 1.414 and the damping factor is 0.177. Then we have to determine value for overshoot, rise time and settling time. So formulas already we have seen. For maximum overshoot, what is the formula? 100 into e raised to minus pi zeta divided by under root of 1 minus zeta square. So here zeta is 0.177. So that's why answer is 58.16%. Okay. Now second formula is 2% settling time. So TS is equal to 4 upon zeta omega n. So we have to put here value of zeta and omega n. So settling time is 15.98 seconds. And third is rise time. TR is equal to 0.8 plus 2.5 zeta divided by omega n. So after putting values, we'll get answer as 0.88 second. So like this, we can find answers for time domain specifications. So like this, we can perform time domain analysis of the system. So thank you so much all of you for watching this video. Now we'll study effect of damping and natural frequency in time domain analysis. So the response of system depends upon damping and natural frequency. As we have already studied, damping is zeta and natural frequency is omega n. So response of system depends upon damping and natural frequency. So what happens? Settling time and rise time of the system reduces with increasing natural frequency omega n. If you increase natural frequency, automatically settling time and rise time will get reduced. Also, as damping decreases below 1, the response overshoots and oscillates about final value. If damping value decreases below 1, what happens? System overshoots. There will be many peaks will be there. Okay. So the smaller the value of damping, larger the overshoot and longer it takes for the oscillations to die. Means if value of damping is below 1, that is 0.5, so there will be larger overshoot and it will take long time to get stable. Okay. So here also you can check with the help of graphs. So the graphs are shown for different values 0.1, 0.2, 0.4, 0.71 up to 2. Okay. So the blue colored you can see check. So this blue colored part is having maximum overshoot because its zeta value is 0.1. So there is very less damping. So as you go on increasing zeta value up to 1, so you can check this red colored part 1. So it has only I think 1 or 2 peaks and it gets stable. Okay. So from this graph you can check that as you go on increasing value of zeta up to 1 or up to 2, the system takes 1 or 2 peaks and gets stable very early as compared to readings of 0.1 and 0.2. Okay. Now here effect of natural frequency on system response is shown. So if you check first graph, the frequency value is between 1 and 2. Sorry, omega 1 is 2. What happens here? The system takes some peaks and then gets stable, but it takes some large time to get stable. In second graph you check frequency value is 4. In third graph frequency value is 6 and in fourth graph frequency value is 8. So as you go on increasing frequency values, what happens? The system takes few peaks and gets stable very early for higher number of natural frequency. Okay, so for last graph you can check after some peaks system gets stable. So here rise time and settling time is reduced. Okay, so like this there is effect of natural frequency on rise time and settling time. System gets stable when natural frequency is more. Okay, so thank you so much all of you.